Okay, so good afternoon, everyone, and welcome to this year's Christmas lecture by the School of Mathematics and Statistics of the Open University. I have the honor to be your host of today's session, and I would like to welcome our speaker, Dr. Sophie Car. She's the founder and director of base consulting, and Sophie's first love was Lego, then aeroplanes, and then her career followed suit. She trained as an engineer, and whilst working full-time, she took a PhD in Bayesian belief networks, and she has worked also in data analytics ever since. Now, or to put it another way, Sophie has made a living out of finding patterns. And outside of her work, Sophie is the Vice President for Education and Statistical Literacy at the Royal Statistical Society, and the world's most interesting mathematician. The title of her talk today is How Can Data Science Help You at Christmas? So again, welcome very much, Sophie, and we're all looking forward to your lecture, and please go ahead, the stage is yours.
Thank you very much indeed. It is really, really lovely to be here. So yeah, my name's Sophie and I like statistics and maths. Did train as an engineer, always loved aeroplanes, still love aeroplanes, didn't think anything would be better. But then I found statistics in my mid-20s and that's been really my career ever since. So I was asked to think about how I can show you how data science can help you, because data science is the term people seem to want to use instead of maths and statistics. But I run a data science company. All the tech team have maths and stats degrees because that's what we need to talk about. But our tagline is maths, not magic, because we can explain a lot about what we do. But at Christmas, you just need a little bit of magic, don't you? So I went on, as seems to be the answer to a lot of things these days, and said to ChatGPT, how do mathematicians decorate Christmas trees? And it came up with some of these solutions here. So we've got the Fibonacci series on the left, and we've got triangle numbers. I'm not entirely sure they're triangle numbers, but they're sort of placed in a triangle on the right. It kind of had the right idea. But decorating a tree is a really serious business, and you will be pleased to know, or not, that actually there is a thing called trigonometry, and there is a genuine formula. And it doesn't matter if the tree is real or fake. It seems to depend on the height of the tree, or at least that is what the students from the University of Sheffield, it's a genuine paper, you can go and find it. They came up with these formula about how you should decorate your Christmas tree. And really you can see the height of the tree is there, and it tells you how many baubles you need, how much tinsel you need, how many lights you need. And if we go for a tree of 25 metres, that is about the height of the tree that you're going to see in Trafalgar Square, the big one that comes over that's been put up this week. You're looking at about 515 baubles and over 100 metres of tinsel. So quite a lot. But it doesn't start to get to the heart of Christmas. So it doesn't tell you if you should have a theme, or if you should go multicoloured, and where the baubles should be placed, or do you go rogue and just put them wherever you want? All those debates that you sort of have in Christmas households over the years. But it does start to show and some of those patterns that I've really enjoyed finding throughout my career. Now, when people talk about patterns and numbers, and actually a lot of maths isn't really numbers, because there is a difference between maths and numeracy, there really is, and we're talking a bit more about maths today, but we are going to do some numbers as well. It's, well, where's the magic? Where do we see it? And I think it's easy to forget that actually you see maths in all sorts of places. So Harry Potter at Hogwarts, well, the students can learn about arithmancy, which is how to predict the future with numbers. Now, in our world, we call them predictive algorithms. They have a mixed reputation. If we start talking about things like machine learning and AI, then we start to worry about ethics and bias, and perhaps we can't always really explain what those algorithms do. Then there's the simpler equations, not necessarily simpler, but maybe regression where we can. Now, maybe you're not a Harry Potter fan, maybe you are a Twilight fan. Okay, so if you've seen the films or read the books, you know that Alice Cullen, she has the gift of premonition, which is seeing into the future. she focuses on a person and she sees what might happen. Now, it's not a predictive algorithm in the way that arithmancy is, but it's actually spotting patterns, and it helps her develop choices and evaluates decisions. So that's much more, to me, at the heart of mathematics. It's helping understand what might, could, possibly. I don't really deal in certainty. As a statistician, I've spent a lot more time in the uncertain realms because that's where all the really fun stuff happens. Now, there's also solving puzzles. Okay, and if you're a Marvel fan or maybe a comic fan, what questions do you ask? It's about actually going in and having that curious and inquiring mind, seeing what questions need to be solved. I've worked in engineering, I've worked in applied maths, I've worked in statistics, and looking across that, the thing that binds all of those mathematical sciences together is a love of puzzles. It really is. It's that just little innate desire to go and have a look and try and solve something and not want to give up until you've solved it and you understand it a bit better. So when we're working in data science, one of the really big things is how we can start to build trust. I've talked about the ethics and I've talked about some of the bias that people see, because what we don't want is people to think that what we're coming up with is fiction or fantasy. It's that what we've got is robust and it's defendable. But it is Christmas time. And whilst I said we do maths, not magic, it's true that maths isn't magic, but we are at Christmas and we need a little bit of magic just to get us through to the end of the term and onto those holidays. So we're going to have a go at some really cool maths together, and hopefully you've got a pen and you've got a paper. If you have answers or questions, pop them in the chat. Hopefully my assistants will read them out if there's anything that you need clarification on as we go through. But what we're going to start with is, how can maths actually help you work out if someone has seen Santa? And by this, I mean the real Santa Claus. What is it that we have to start with? What is it we have to understand to make sure if they've seen them? Well, I'm going to say there's three things we need to work out, okay, or three things we need to have an understanding of. Firstly, it's how many students will see the real Santa, the real Santa. Of those who see the real Santa, how many are going to say that they did? Equally, how many people who haven't seen the real Santa are going to say that they've seen Santa? Okay, and those sound sort of fairly easy things to get our heads around, but it's how we combine them and then what questions we actually want to ask. So I'm just going to put some numbers to this, and then I'm going to ask you a couple of questions, and we can start to see gut instincts and how sometimes our gut instincts might let our maths down a little bit. Okay, so how many students will see the real Santa? So I'm going to say it's about 1 in 500 students. So about 3 maybe in a standard secondary school will see the real Santa. Of those, 95% will say that they've seen Santa. But about a third of students are going to say that they've seen the real Santa when they haven't. It happens. So let me ask you 2 questions. They're similar, but it's the way we say them that's important. So what's your gut instinct that you're going to see Santa, the real Santa? And what's your gut instinct that if someone says they've seen Santa, they've actually seen the real Santa? So with those numbers, and you might look at these and go, oh, I've sort of heard some of these terms, or I've heard similar things in terms of COVID testing. Yeah, you will have false positives, false negatives, those types of words. So have a think and just write those down. 2 questions. Firstly, with those numbers, what's the gut instinct that you see the real Santa? And secondly, what's your gut instinct that if someone says they've seen the real Santa, they actually have? Now, the answer to the first question of what's your gut instinct that you'll see the real Santa, it's about 5%, which isn't too bad really, all things being equal. It's probably higher than you were thinking. But if somebody says they've seen the real Santa, what's the chance that they really have? Well, that's about 3%. It's a bit lower. It's still quite high considering how busy Santa Claus is, and we're going to get onto that and do some maths on that later on. But it's quite hard for people to combine numbers in their heads, and it's actually quite hard for people to combine probabilities in their heads. So before we get on to some of the really cool stuff a bit later on, we're going to do a quick recap. talking about the vegetables, I love growing my own vegetables. I'm not stunningly good at it. I will admit that here and now. But I genuinely have kohlrabi and kale growing in my garden. I've got some leeks there, and I'd like to say I've got a red cabbage, but it's really small this year. The pigeons got to that one. However, this is the best representation that I can come up with. So on the right hand side, you will see that I have got the leaves of every vegetable I grow for Christmas. And on the right hand side, the copper bands that I was absolutely assured stop snails from getting to my cabbage leaves and my other green leaves, my kohlrabi. Now, I will say now, if you have ever tried those copper bands, you will know that this is what you're meant to see. So what you've got here is an 8x8 grid, my raised beds, okay? And on the area I've drawn, we've got 40 out of those 64 or 62.5% of that area is leaf. And the remaining 37.5% is the copper band. Now, that whole space sums to 1. Okay. But what's really important to understand is that there are 8 snails. But they're not necessarily part of the probability space that we're defining. Okay. So if we want to say what's the probability of a snail being on a square, then actually we might want to condition that. So it's what's the probability of a snail being on the leaf? Or what's the probability of finding a snail if I'm only worrying about the copper band? Or what's the probability of finding a snail on a square if I'm talking about the whole area? And it's actually interesting in answering these types of questions that helps us understand if that base number for our probability that we're calculating, is it the 40? Is it the 24? Is it the 64? What is it that we're actually worrying about? And the reason for saying this is that the language of mathematics is incredibly precise. And it's easy to forget, because if you love numbers, you might not like writing so much, that at the heart of mathematics is the ability to write. Andrew Wiles, who solved Fermat's last theorem, there's a film about him. And at the start, he talks about how maths and solving a maths problem is like sitting in a totally darkened room, and you stumble about because you don't know what you're doing, and then you almost by luck or by chance you flick on a light and you've got a bit of illumination that gives you an idea of where to keep going, and then you switch on another light, and at some point you've got complete clarity and the room is lit. But he goes on further in the film to talk about how mathematicians are inherently very cautious, because we spend a lot of time working on a problem, and when we think we've got a solution, we write it up and then we publish it and we put it out there. And once you've put something out there, you can't get it back. And I think that's probably a pretty good rule to think about, actually, when you use social media generally. But it's that type of nature of the very precise language, the very precise nature of mathematics about how we choose to write things that is at the heart of a lot of the maths that we're going to talk about today. And just in case you're wondering how great those copper bands are, this is actually usually what my vegetables look like. I would be certain that the local gardening organisation, the Royal Horticultural Society at Wisley, actually probably come and put snails in my garden. The copper bands have not worked at all. Now, more importantly, how can maths help you maximise your chances of actually getting the present you want? Okay, so for this is where you are going to need your pen and paper. We're going to define a few assumptions. We're going to have a go at solving how Jingles, here on the left, can actually maximise his chances of getting the present that he wants, which in this case is a magic pot of sweets that will refill throughout the year. Okay, there are 3 presents to choose from, red, green and purple. So if, to be clear, the red, it will always be at the top, and that has the diagonal stripes. The green will always be in the middle, that has the horizontal stripes. And the purple gift is at the bottom, always, and that has the diagonal wrapping paper, the little diamond wrapping paper on it. Okay, so we've got red, green, purple, which is diagonal stripes, horizontal stripes, and the diamond shapes on it. Okay, so Jingles is going to get to choose one of those 3 packages. Okay. Father Christmas will open one of the other packages, okay, that he hasn't chosen. That will leave one unopened package. Jingles has to decide whether he sticks or switches. Now, we need to work out what's the best option and why for Jingles to maximise the chance of him getting the sweets. The other key thing to remember about this game is that Father Christmas will never open the box that has the sweets in, okay, because that would spoil the game and Jingle would win, and maybe Father Christmas doesn't want Jingle to win. Okay, so here we go, quick recap. 3 presents to choose from. 1 has the sweets in, which will magically fill all year. 2, they're empty. It's going to be a sad day for Jingles if he gets those. He chooses 1. Father Christmas opens one of the other 2. Okay, should Jingles switch or not? So now I'm going to give you a minute. What I want you to do is write down all of the things you think you might want to know in order to help Jingles work out whether he should stick or switch once the other present has been opened. And I just want you to think quite broadly about this. What is it that you think you might need in terms of numbers? What assumptions are you going to be making? How are you actually going to be able to answer this? Have you got an idea of the maths you might want to use? Can you start to sketch out some ideas? Just spend a few seconds just generally having a think about the type of questions you would want to answer, because as you start to write those down, that's often how you can start to formulate things. When we do coding in my company, we don't just start coding, we actually structure the code. We put all the headers in about what we think each section is going to do and how we think it might flow. And then we start to put in bullet points about what those sections are going to do. And only then do we actually start doing some of the really fun coding. We all like coding in my company. I'm not particularly good at it. My code tends to be very long, and the people I work with can take my long code and make it about this big. But anyway, so hopefully by now in that minute, you've managed to write down some ideas about the things you'll want to know. Okay, so what do I think Jingle will need to know? Okay, so I've got these few points. The first one we're going to have to worry about is which present Jingle chooses. Okay. The second point we need to work out is something called a prior probability. Okay, and that's the baseline number or chance that the sweets are in any of those boxes. Okay. The third thing, is the conditional probability, and that's the probability that Father Christmas is going to open the present where the sweets are hidden. And then we need something called a marginal probability, which you may or may not have heard of, depending on how far you are through any stats studies that you've done. And they're called the marginal distributions because we tend to write them in the corners, literally in the margins. And what we're going to work out there is just the chance that Father Christmas will open one of the boxes. Okay, so I'm going to start by having a quick discussion about a prior probability, that baseline, that background one, because my guess is you might have an idea. But in Bayesian statistics, prior probabilities are crucially important, like really, really important. And they separate out Bayesian statistics, which is the thing that I really, really love, from frequentist statistics. Now, the best way to describe the difference between Bayesian and frequentist is it's rugby. So I grew up in the north of England. There was only one code, rugby league. It was Wakefield, was our local big rugby union club when I was a girl. I went to university in Bath to do my undergraduate degree, and there was only one code, and it was union. Pretty different to league at the time. And both are rugby. Both have utterly avid fans. Both absolutely, people will tell you that theirs is by far and away the best approach, but actually they love the game of rugby. Okay, so that is the difference between Bayesian and frequentist at quite a high level. It's both statistics. You will see people tell you that frequentist is better than Bayesian or vice versa. And the truth is you need to use the right approach for the problem that you're trying to solve, so long as you stick with the approach that you use. But it's actually, in Bayesian statistics, a prior probability is actually quite a really lovely philosophical debate. And you should be able to define a prior for everything. Now, in an ideal world, maybe there would be data for you to find that prior probability from that you can go investigating. But the truth is, sometimes we don't have reams of data to go through. Sometimes you have to go and talk to experts and get their opinions and get their views and elicit from them what they think this number, or even better, a distribution, might actually look like. And how we use that precise language, how we get to extract the numbers or the distributions from people, actually is when biases start to come out. So people's ability to recall numbers. So, for example, often if you just talk to anybody, they will overestimate the likelihood of relatively rare events like volcanic eruptions, because when they happen, they make the news. There's also something called the availability heuristic. So that's when they see it's written up a lot, but recall, how many examples of that have I seen? Oh, I've seen them quite a lot, because they're in the news. When actually volcanic eruptions are quite rare. Now, there's also the chance that people might go, oh, well, do you know what? I just don't know any different. So all I'm going to do is assign the same probability to everything. So if I've got 5 things that might happen, I'm going to make each one of them a fifth. That's called a flat prior. And in some circumstances, that's the right thing to use. But in real life, that always makes me slightly nervous, because what that means is, has somebody just taken the easy approach? Have they really thought about the differences in these events? Because defining the right priors is absolutely crucial in Bayesian statistics. Much of the deep debate about Bayesian analysis links the use of the definition of priors. But to me, it defines how the mathematicians have actually thought about the problem before they go and try and solve it. So that's what prior probabilities are, and that's why Bayesian statisticians really care about them and spend a lot of time trying to come up with what they are. So if you quickly sketch out this box, okay, for the 3 gifts that we've got, what is the probability of the sweets being in any of those boxes, and why are you assigning that probability? You sketch that out. You can come up with a group answer if you're doing it in the class. Maybe have a chat to your neighbour if you've got one. Maths is not an individual sport. It really, really is done in teams. It really is a collective effort to advance people's knowledge and work on problems. Yes, I know when you're doing exams right now, it might look like it's an individual endeavour, but as you carry on, you'll find that actually working in maths is a really lovely collaborative career to work in. So if you've sketched that out, you can put RGP, or you don't have to match it up exactly. What's the chance? Well, having said that, actually flat priors make me inherently very nervous. With no other information, we can actually say it's a third. Now, it might be that if you saw Father Christmas students every year, you may have knowledge that says actually he tends to hide it in the green box, or he tends to hide the sweets in the purple box, and that's the one I'd always go for. In which case you wouldn't put a third here. But with no other knowledge that we have, in this case, it's kind of right to assign a flat prior to each of them. Now we have to worry about which gift Jingles is going to choose. Now, again, we haven't really got any information about this, so I am making a judgment call, and I'm going to say that Jingles is going to choose the gift that matches his hat. So he's going to choose the red box for no other reason than it matches his outfit, which seems as good a reason as any. I've got my Christmas jumper on today. I'd have gone for the red one too. Now, we get to talk now about the absolute wonders of conditional probabilities. And these are genuinely fantastic. So to help with our maths, we need to choose a present to condition of, just so we've got something to hang our hat on, just so we've got something to help make the maths a bit easier. Okay. And so I'm going to say that Father Christmas, we're going to talk about Father Christmas opening the purple box. I could have chosen the green box, it wouldn't have made any difference, but I'm going to say we're going to worry about doing the maths for Father Christmas opening the purple box. Okay. And that now gives us something to question, which is, what does it mean in terms of the present that can be opened in front of Jingles? Because that's how we're going to calculate some of the numbers we're worried about. But we are at this point now talking about conditional probabilities. Now, probabilities as relative frequencies has been sort of the dominant for quite some time. Now, conditional probabilities are actually quite hard to grasp, and you might go, oh no, they're dead easy, they're just the two arms of a decision tree. But when you really start thinking about them, conditional probabilities actually overlap with causal reasoning and causal thinking. So I've talked about language quite a bit, but all of the differences around language, and that includes emotion, because it's really easy to forget that maths is an emotional subject. And I am not talking about whether everybody should do maths to 18 or I hate maths and I never want to see it again. I'm talking about the fact that maths drives social change. Okay, so it's facts such as a third of all children grew up in poverty before the cost of living crisis, that less than 25% of all women are FTSE board members. Okay, it's those type of numbers that make you go, what? No, that can't be right. And it drives social change. Maths is an incredibly emotive subject for all the right reasons, as well as the fact that some people don't like it. But when we start to talk about a conditional probability, actually empirical research shows that variations in the wording of the question, variations in the format that you ask for the data for. So are you asking people to write down an absolute number or a proportion or a percentage or a probability or to draw a shape? Even within the context of the actual problem alters the way that somebody can engage with that question and give you an answer. All of their inherent biases that they might not even be aware of come into play. Okay, and that affects the result that you get. So you also need to think about what a probability statement means. Genuinely, are probabilities out there in the world like a frequency? Or are they an objective feature of reality? Or are probabilities just in our heads as some sort of subjective degree of belief? And how can we actually calibrate a subjective degree of belief? So if you take the principle of something called the principle of direct inference. So if you know a coin is fair, then you're going to assign a belief of a half that you would get a head or a tail if you flip it. Now, that seems really obvious because you probably just accepted that that's what you do. But I want you to think about what it really, really means, because conditional probabilities are most commonly defined in terms of unconditional probabilities. But the thing is, when you do an experiment and you record an observation, okay, that is exactly what you're doing. You are observing something which is conditioned and affected by everything you've done to make that experiment happen. There'll be things that you maybe can't control or haven't thought of. So instead of defining conditionals in terms of unconditional probabilities, should we really be defining the unconditionals in the terms of the conditionals? And that is what really cuts across the difference between Bayesian and frequentists in terms of debate. So if you want to get to the heart of Bayesian statistics, and it is, by the way, an absolutely amazing subject, which has given me, it's just given me a life I never dreamed possible. You really need to have a think about conditional probabilities. And if you're thinking, well, I don't really care about Bayesian statistics because when am I ever going to use that? I can use some really simple examples. Turbo code, the thing that gets you the 4G in your mobile phones, that's Bayesian statistics. What drives the Google search engine? Yeah, it was Bayesian statistics. The thing that works out your test results, Bayesian statistics. What calculates your insurance premiums if you're trying to get a car? Bayesian statistics. This amazingly small, stunningly powerful equation rules most of your everyday life, and it's probably something people have never heard of. But at the core of it are these things called conditional probabilities and a prior. And understanding how those change your life, I would suggest, is probably time well spent. Now, to get you to do some more maths, you need to draw out another 3x3 table. So now we've got to answer a question. We know that Jingles is choosing the red box. Okay, but we have a different question to answer here. If the sweets are hidden in one of those boxes, then the probability that I or Santa will open the purple box is what? And what's going to affect your decision for giving the probability there? So I'm just going to give you a minute or so to have a think about that. If the sweets are hidden in the green box, what's the probability that Santa is going to open the purple box? Okay. Now, you need to remember here 2 key things. Jingles chose the red box, and Santa can't open the box with the sweets, because that spoils the game. So, have a think for a minute or so. What probabilities are you going to assign to these to answer the question? If the sweets are hidden in a box, what's the probability that I'll open the purple box? And then just write down your thinking. Again, chat to your neighbours, chat as a class. If you've got any questions, pop it in the chats, and hopefully my assistants will let me know. But it's an interesting one, because this really starts to get to the heart of the condition of probability. We've not seen this, but I'm guessing Santa does this every year. Equally, what would make you change your answers? These are the types of fun debates you get to have. I think they're fun anyway. I find them immensely intriguing. But have a think, and we'll give you another 20, 30 seconds, and then we'll see what I've got, see what answers you've got, see why they differ, and then we'll try and work out how we can help Jingles maximise his sweets, because who doesn't want me filling sweets for you? It's quite a good answer, isn't it? So you've had about a minute since I told you to start thinking about it. And if you've not got an answer now, just pop down what you think it might be. It's okay to get it wrong. I spend most of my time getting my maths horribly wrong. And I'm right not that much of the time. But when I'm right, we figure out how to go forwards. Okay, so I've got this. If the sweets are in the red box, and that's the box that Jingle chose, then actually Santa can open the purple or the green box equally, because neither of them have got the sweets in. Okay, so what that means is there's about a 50% chance, half, that the purple box is opened. The fundamental assumption here is that we have no other information, or we don't have anything else to change that belief. Like I say, if you saw this year on year or month on month, you might start to think, well, actually, Santa generally opens the green box, and that would change that half distribution. If the sweets are in the green box, if the sweets are in the green box and Jingle has chosen the red box, well, Santa has to open the purple box. He's got no other choice. No other choice at all. And puts the probability to 1. Okay. If Jingle's chosen the red box and the sweets are actually in the purple box, well, we can't open it. There's nothing we can do, because that spoils the game. So again, these are all dependent upon the things that Jingle has chosen the red box, and Santa cannot open the box with the sweets in. So if they're in the red box, 50-50 chance that Santa will open the purple or the green box. If they're in the green box, he has to open the purple box. And if they're in the purple box, Santa just can't open that box. So how do we start to work out the probability of Santa just opening the purple box? That background probability, it's not quite a prior, it's called a marginal. How do we do that? Well, we do it with one of the most underrated tools in mathematics, the glorious and wonderful decision tree. So here's my next task. Sketch that out. Red, green, purple. Like I said, same order throughout. And what I want you to do is write down the probability of the sweets being in the box. That's our prior. And then the probability that I or Santa will open the purple box. Now you've got those probabilities. And like all good probability trees, we need to fill those in, multiply up the arms. Okay, so have a go, sketch that out. Again, I'll just keep chatting. Obviously, you've got about a minute to do that in and have a think. It doesn't have to be a perfect representation, but see what you can come up with. And it won't be the same probability on each final arm, but it is get you to think about those wonders of conditional probabilities, which are, yeah, they're just really cool. And hopefully by the end of this, you'll go away either thinking, yeah, I really should think about a bit more. I don't know what she was talking about. I don't want to hear about those again. But stats is really cool like that. So hopefully you've sketched that out. And maybe you've looked at the numbers we came up with in the back and what you've actually come up with is something that looks kind of like this. Okay, so they're all from the tables that we've seen over the last couple of slides. Okay. So now I've got 3 questions that I need you to try and come up with the answers to. Okay, and they're this. So again, how can we answer the question? The probability that I or Santa will open the purple box, given the sweets from the red box, then in the green box, and then in the purple box. So if you come up with the answers for each of those, okay, and then actually, I want you to think about how you might go about calculating just the marginal probability, just that probability that Santa opens the purple box. How do you calculate that once you've answered those 3 questions? So follow the arms of your diagram and answer those 3 questions. And then when you've answered those 3 questions, how do you answer the question, what is the chance that Father Christmas just opens the purple box? Marginal. If you're not sure, we've talked about timesing up the arms, and then if you remember your GCSE statistics, you times up the arms and then you add down the side. And the way that we actually in this case come up with the marginals, there we go, is we add down. Okay, so we've now kind of got most of what we talked about, but what we haven't answered is, should jingle switch? And that's actually involving us flipping round the question. So we've been asking about the probability that a box is open given the sweets are hidden in it. But actually what we want to know is, where do we think the sweets are given that a purple box is open? And it might sound quite simple, just changing the order, but actually it really alters how we look at those probability trees. And Bayes' theorem, for all its amazing uses, like I said, getting your mobile phone signal, driving your search engine, and a bunch of other things, actually you flip the arms on the probability tree. That's all it is. And I know that sounds so simple, but you sort of flip the arms and you recalculate, and that's where the wonders of Bayes' theorem comes in. And this is Bayes' theorem. Okay, now it's the only equation in the whole presentation. Okay, you don't need to worry about it. But what you're looking at there, the top line, is the total law of probability. And the total law of probability is used when you don't know the probability of an event, but you know its occurrence under disjoint scenarios. Okay, and that means they're mutually exclusive, so they can't happen at the same time. So that top actually considers all the possible events, but we don't want to worry about all the possible events. We want to focus on what happens when the purple box is opened. So to do that, what Bayes' theorem does is it renormalizes the total law of probability by the probability of the purple box is opened. So that is Bayes' theorem. That's it. It's really simple at its simplest, like this. 3 things, we times 2, we divide by 1. It's not hard. The really complex bit is actually worrying about the conditionals and the priors and have you got those right. Actually, the equation, it's quite simple. You can make it more complicated by conditioning on different things, but at this level, it's actually the conceptual part that's a lot harder. So if we now need to work out the probability the sweets are in the box, given that Santa's opened the purple box, what we need to use now is Bayes' theorem. And the way that we do that is we take what we had last time, so you multiply along the arms, and then we normalise by that half value. We normalise by the unconditional, that marginal probability of Santa just opening the purple box. And that's the only difference. Okay, so if you've got your previous sums from last time, all we're going to do now is put in that renormalisation factor. And lo and behold, this is what we end up with. So if jingle sticks with the red box, he's got about a third chance of getting the sweets. If he switches, he doubles his chance, about 2/3. That is not to say that if he switches, he will always get the sweets. He just increases his chance. And if he's seen Santa doing that enough, he might decide that, yep, Santa always prefers the green box, or nope, it's generally matching Santa's outfit and it's in the red box. So personal biases may come in, but on the whole, if you are offered the opportunity in that game to switch your boxes, switch, because you've got double the chance of getting some sweets, which is probably a good thing around Christmas. So we've talked about how Bayes' theorem can help you work out if Santa is actually real, or you've seen the real Santa. It can also help you work out how you're going to maximise the chances of getting the sweets that you want. But there's some other cool math that can help you with Christmas, aside from trigonometry. And we're going to have a quick chat about how Father Christmas manages to get all the presents to where they need to be across the world. And this actually, in some ways, at the end starts to hark back to that first thing I studied, which was aeronautical engineering. And actually, my master's is in fluid mechanics and applied maths. And I generally thought I was going to work in that for the rest of my life until I found statistics. So let's start worrying again about those baseline assumptions that we have to make when we're answering maths problems. So there are about 1.3 billion adolescents in the world. It's about 16% of the world population. Okay. And there's about 2.3 billion homes in the world. So 45% of the world celebrates Christmas in some way or another, which leaves us with about 0.65 billion adolescents to worry about, 0.65 under 18s. And I'm only worrying about under 18s. The adults can sort themselves out. And we're going to say that's about 500 million homes, roughly speaking. So the first real question is, are all of them on Santa's list for having presents? And we're going to say yes, just to keep the maths a little bit simpler. But these billion homes are actually, these billion homes are actually quite congested. These half billion homes, quite congested, because of all of the world, actually, humans only live in about 10% of the world's land mass. So it raises this interesting problem of, how does Santa get to all the homes that he needs to do? And it's actually quite a famous maths problem. How's he going to do something that looks like this? It's called the travelling salesman's problem, or the travelling salesperson's problem. And it basically asks the question, given a list of cities and distances between all of those cities, and whether they're towns or villages or wherever, what's the shortest route that Santa Claus can take to get to all of those once and return from where we started? So how does he leave home, visit everywhere in the shortest possible distance, and get back? Now, that's something called an MP hard problem in combinatorial optimization. And you might think, well, why do I care? Well, actually, it's a really important part of computer science. And it also forms a large part of operations research. It's a graph problem. It's a mapping problem. And it's actually a common interview, or used to be a common interview at Google, because actually how you route data among data processing nodes, those routes will vary by time to the transfer the data. The nodes will vary by computational power and storage, and you compound the problem of where to send the data. So it's the same approach about how you optimize transferring routing. It's also the same problem if you think it's not got a real life application, Deliveroo. In fact, anybody who's going to be delivering logistics, how do you minimize the distance traveled, but also get to everywhere where you need to be on time? You know, it might even help you plan your route to your Christmas party too. So the other things we need to worry about, well, there's only 36 hours of night, allowing for the changes in the days if Father Christmas goes the right way around the world. So he's got 36 hours to cover 10% of the world's land mass. And now we get to the tricky part. So how is Santa actually going to get into the house or home? How is Santa going to park the car, let alone eat his mince pie and pop a carrot in the bag when he gets back up to feed Rudolph? So really, we've got 36 hours, about 500 million homes. 36 hours is only 129,600 seconds. If people are visiting other families, we're looking at about 800 houses a second, which is quite a lot. You know, Father Christmas has got his work cut out on this night, and he's going to have to be travelling pretty quickly, which is what we're going to figure out next. So the assumptions we're going to come up with are 10% of the world's landmass to travel around, 36 hours, 500 million homes. You're going to have to make some assumptions about the weather. I don't know what you want to put down. That might be starry night, clear sky, no snow. Remember, it's really hot in some places at Christmas and certainly not so hot in others. What about the density of the houses? How does that vary between urban and rural? Does he land 800 homes in a minute? 800 homes a second? Might just choose to hover. How many mince pies eating? You're going to have to take a very strategic decision on eating the mince pies and how you get in and out. So here is my question to you. If you've got 36 hours, 10% of the world's landmass, you are travelling somewhere between 6 and 40 million miles in an evening. How far and how fast does Father Christmas have to travel? So just spend a couple of minutes thinking about that. What I want to know is, how fast do you think Father Christmas travels? This is just simple sums now. Take a number between 6 and 40 million miles, 36 hours. How fast is Father Christmas travelling? It's an interesting problem. And that's before we put on how he's going to actually get into the homes and eat the mince pies. Okay, so as you start to have a think about that one, okay. I mean, you might want to actually think about doing this as a range. That might be one way you want to think about doing it. You might want to think about doing this as a set number, but the range you're worrying about is this. If it's easier, then you're actually thinking about somewhere between 10 to 65 million kilometres to cover in 36 hours. It's quite a lot. So my suggestion is that, well, actually, what I want you to do is, if you work this out in terms of miles an hour, miles a minute, miles a second, meters per second, or easy to get into meters at some point. And the reason for that is we're going to start talking about some of the wonders of aeronautical engineering and something called the Mach number, which is something I had the joy of working with for quite a while. So as you're going through that, what we've got is, if we take the lower end of that, about 6 million miles, then you're about 166,666 miles an hour, give or take, ish. 2,777 miles a minute, or more crucially, 46 miles a second, which is about 69,500 meters per second. And this is where we get to the fun thing called the Mach number. So the Mach number is how fast you're traveling in relation to the speed of sound. Now, the speed of sound obviously varies between whether you're on the ground or quite high in the atmosphere, because it's affected by the density of the air that we're actually operating in. But assuming that Father Christmas flies about the height, well, he's going to have to fly just below the height of jumbo jets, because he's going to need enough oxygen to breathe. Then actually Father Christmas is travelling at about 202 times the speed of sound. That is fast, and that is without assuming that he's going to stop, get out, get the presents in, get back in and go. Okay, so at 202 times the speed of sound, I am going to suggest that Rudolph absolutely doesn't need his scarf, because the amount of friction that Rudolph is going to be going through is an incredible amount, and there will be enough heat created by travelling at the speed, definitely to turn his nose red, and he will be very warm indeed. And let's just hope he protects all the other reindeer while he's at it. So maths can absolutely make sure that Santa can optimise his route, but what it can't do without a little bit of magic reindeer food is make the reindeer travel that quick. And also without a little bit of magic, I'm not sure how Father Christmas is going to find enough time to actually get all the presents into the house and get back out and feed the reindeer all those carrots, which they might need the food to get through that quick. So, as promised, that is me done in 50 minutes, leaving times for questions. I'm going to say thank you very, very much for coming. I hope you've had some fun doing some quick maths and sketching this afternoon. And thank you very, very much for having me. It's been an absolute delight.
Yeah, Sophie, thank you very much for your fascinating talk on statistics and Christmas. And yeah, so let's open the Q&A session now. And I welcome any questions on your presentation, Sophie. Any questions from yeah, please go ahead.
There might not be.
I believe we have some questions here in the chat. Just give me a moment. Okay. So maybe while the students are looking for some questions, so maybe I start with a question of my own, if that's okay, Sophie.
Yeah, that's okay. That might not be anything.
I was very much interested. I find your example on choosing the right Christmas present very interesting. So is this kind of related to the Monty Hall problem?
Absolutely. It's exactly the Monty Hall problem. And I think the Monty Hall problem is one of those things where people inherently sort of know that they should switch, but don't really know why they should switch. And they don't really understand how come you get double the chance. And I think it all comes down, like say, to that normalization. And I think it's really it's really important that people understand how being able to do some maths in your head, or at least have an idea of being able to do that, actually can really, really help you. I think if we got to, oh, hang on, Ben Hawk. So I was concerned at how many mince pies Santa eats. I would suggest that if Santa is trying to eat the best part of 500 million mince pies, that could have a substantial impact on his weight over the course of a 36-hour period. But yeah, I'm with you, Ben, on that one. Next one. Which companies would be interested in recruiting students who have a data science degree? Okay, so that's a really interesting question, actually. And I would say that there are an increasing number of companies who look for data science degrees. I will say that you're going to have a really good think about whether you want to do maths, statistics, or data science, because data science covers a massive range. And there's an organisation called the Alliance for Data Science Professionals. And you will see that that's made up of the British Computing Society, the Institute for Maths and its Applications, the Royal Statistical Society, and the Operations Research Society, all of whom have data scientists, but all of whom also have computer scientists, applied mathematicians, statisticians, and operational researchers. Data science is a catch-all term for an awful lot of different disciplines. Now, at the heart of it is that problem solving and that structuring and the assumption making and the model building. So a lot of companies will look for that skill set. What you maybe want to think about is, do you want to do a slightly more fundamental broad degree, such as maths, statistics, operations research, and then a master's in the area of data science that you like? So my company's data science, but I hire mathematicians and statisticians. They work as data scientists. They like that title. Data engineers, I have software engineers, but they all did maths and stats. I know other companies, and I would hire a data science degree, but our data science does a lot of maths and stats. I know other companies do data science who need coding, but not necessarily as much maths and stats. So find the bit of data science that intrigues you the most, and then find the degree that suits it. Or the degree apprentice. I would say there's some amazing data science degree apprenticeships out there. Oh, thank you. I'm glad you liked my Christmas jumper. You can't see it actually flashes. It's got Christmas lights on it, but I'm afraid you can't see that part. So I'm glad my Christmas jumper's been useful.
All right. Okay, are there any other questions from the participants?
Maybe not. Maybe they're just all learnt to love statistics so
Maybe
much
not.
that.
Maybe.
Yeah, that's okay.
Okay. So yeah, again, Sophie, thank you very much for your very interesting talk. And of course, we also wish you a very, very happy Christmas, very Merry Christmas, and all the best for yourself and your
Same
company.
Thank you. Yes, we have our company Christmas do next week, and we are going to the board game cafe.
Yeah.
So we're going to have a good time there.
All right.
Thank you very much for having me. It's been lovely to meet you all.
Thank you very much, everyone. Thank you.